Okay, I'd like to look at page 296, C1. So we want to find a proof of this implication. Now they say the book says these require IP, so they require indirect proof to accomplish. So what they're saying we have to do is assume the negation of the conclusion, and then arrive at a contradiction, and then use the IP rule, which I should remind you, this rule, I assume the negation of what I want in the end, and then I end up at a contradiction, then I'm allowed to arrive at the original thing. So we have to assume this, and we'll assume the negation of this, and then we'll see where we end up. So we'll have to use the negation of a quantified statement to complete this. So here's line 1. I have the base assumption for all x, ax implies b. Then one level deep, I'm going to make my excuse me. I'm going to make my negation of the there exists, negation of the conclusion. Ax implies b. And that's an assumption. And so now I'm ready to do my proof. Now this will depend on the rules for negating statements with quantifiers. And we've talked about this in a previous video. But let me show you the rule. So we want to negate a there exists. Oh wait, that went too far. Proofs with quantifiers. Well, I'm going to go ahead and say we're allowed to use these rules from the next section because it makes it so simple. And if you watched all the videos for this week, you would have seen these. So let's go ahead and allow that. So this is the rule of conversion of quantifiers, CQ. So by the CQ rule, I can say that this negation of there exists of some formula, okay, is for all x, negation of that formula. So this is really for all x not ax implies b. And you need to be careful about those parentheses, okay? That negation has to hit the entire formula. It doesn't hit only the a, for example. So it's just like in algebra, when you're squaring something, it squares the entire thing. It doesn't square the first term or the last term or something only. So that is the CQ rule, and it according to this documentation, it just cites the line 2. Okay. Now, I can use universal elimination to take the line 1, and I'll pick some constant, maybe little c, and say I can get little c implies b. That's universal elimination on line 1. And in a normal semester I probably wouldn't let us use CQ, but nothing about this is normal during the virus, so let's just bend the rules a little bit. Allow us to use CQ. Now I will use universal elimination on line 3, and because that's universal, I am allowed at this point to pick the same thing, right? So I get negation AC implies B, and that's line 5, and that's for all elimination on line 3. Well, okay, of course we have a contradiction, right? I mean, we have something and its negation, and what was that called? Negation elimination. This rule here. If I have something and its negation sort of appearing earlier in the proof, then I'm allowed to say, well, contradiction, that's a problem, trouble, and that's negation elimination. Nope. Negation elimination, and I have to cite the negated thing first, so that would be line 5 and then line 4. Well, according to the IP rule, since I started my subproof with a negation of something and I ended up with a contradiction, then I'm able to conclude the the thing that wasn't the non-negated thing. So I can conclude there exists X, AX implies B. That's line 7, and that is IP on the subproof from 2 to 6. Now, the book does talk about how the CQ rule is a derived rule, meaning we should be able to do it without doing the whole proof, but how would we have done it, I guess, is a good question. Probably we would have had to assume this, and then we could have concluded B from that. We could have also concluded like A of C, and then I'm not sure, okay, but this way was easy, so it works. But you might want to think about how you would do it without using CQ, but it would boil down to embedding a proof of CQ into this proof, probably.